Microphone, shall I?
For introducing me.
Oh,
So,
sorry.
Microphone.
oh, microphone.
Thanks.
Where is
Shall I?
You could hear me from my hotel room.
Okay. I hope it works. Yeah, seems to be. Actually, I've changed my affiliation. I am living now in Kühlungsborn, and this is an advertising to spend holidays there. Okay, this is an institute for atmospheric physics, and we are dealing more or less with middle atmosphere dynamics. And it is also good if you can simulate gravity waves propagating in the middle atmosphere. And as we heard yesterday, if you need a very good representation of gravity waves if you want to learn something about the middle atmosphere. And for instance, if you have too large off-centering in your implicit scheme, then you will not get the right waves. So Kevin told us yesterday about this topic. But next slide. But this talk is not focused so much on non-hydrostatic dynamics and also not about Poisson brackets. So I bothered you with that last times at PDEs on the sphere. Actually, the ICON model is a model on an icosahedral grid. And the main grid boxes are hexagons, in fact. And it is very natural that we say, OK, the divergence lives indeed on this hexagons here, and you have to invoke the theorem of Gauss to compute it. So, but what is not yet understood correctly, but I don't know whether it's really understood, or perhaps I only think it's not understood, that the question, where indeed does the vorticity live? Does it live on one triangle, as we suppose, and as we saw this week, I think 3 times at least? Or does it live on 3 rhomboids? So I tried to point or to color these 3 rhomboids in green. If you look at this rhomboid here, there's a green rhomboid, and then there's a yellow one here, and then there's a red one here. And in fact, the vorticity would be located at the corner of a hexagon. This is the case in both approaches here. And my talk is about, I want to advocate for the 3 rhomboids here. And why do I have this idea? I will explain you in 3 examples in this talk. First, I will tell you something about the dispersion relation, which is more or less a repetition of John Seburn's 2008 paper. Then I will tell you about the momentum diffusion and also tell you something about that if you diffuse kinetic energy, you have to re-enter it to the internal energy, so for being energetically consistent. And this is only possible if you use three rhomboids as the dual grid. So what I will tell you later on. And then I found an instability, which was also mentioned this week already by, I think it was Thomas, that there is an instability in the 3D equations, or not in the equations, in the discretization of the 3D equation. And to prevent it, we also need to consider the vorticity on rhomboids instead of triangles. So let's start. So first question is, first example on why should we consider the vorticity on rhomboids, the dispersion relation. So we first try to understand what's going on a regular grid, because I think first we have to understand what's happening on a regular grid before we switch to an irregular grid case and try to reconstruct tangential winds and everything there. We first have to understand what's going on the regular grid, so all equal angles. And we compare it here for a better understanding of all the people who worked with quadrilateral grids. We compare to the quadrilateral C grid. On a quadrilateral C grid, you can write down the shallow water equations. You have an equation for U and for V and for for the geopotential. And it is clear that for the Coriolis term you have to average the V somehow to the point where you have the U component of the wind and vice versa. So in the hexagonal grid you have also one equation for the geopotential height, and then you have 3 equations for the horizontal velocity components. And you see here this tilde averaging, which were invented by John some years ago. And the question is, where do they come from? Why do I have to use a special averaging and not some kind of guess averaging for this kind of reconstruction of the tangential wind? It's because we have 3 wind components here in the horizontal. And if you want to express a vector in the horizontal, you only need 2 components. So you must slave 1 component, which means that these velocity components are linear dependent. And how to prove that they are linear dependent? You cannot prove it for the velocity components itself, but you can prove it for a gradient. If the velocity components are expressed as a gradient, then you can prove this relation here. That for a gradient component, delta 1 alpha, so if alpha is in the centers of the hexagon and the gradient is just the gradient along this line here, that this relation holds only for this special averaging, which averages the gradients to the center of the hexagons. And if you suppose that alpha, for instance, in this case would be the geopotential height, then you can see, okay, the geopotential height in terms of this averaging indeed sums up to be 0, which means that you have slaved the 3 velocity components. So and then you have to inherit this kind of averaging to the Coriolis term here, and that is why these tilde averaging arrive here. This is not the reason because there is some problem with the Coriolis term, but there is an understanding how the gradient term works in fact. So, and if you have inherited this tilde averages, then you see that this, and you sum up these 3 equations, you see that this term here cancels with that term, and that term cancels with that term, and so on. So now we know that these averages are there because of the overspecification of the velocity components. So we can now write down, instead of the shallow water equations in momentum form, we can write down the shallow water equations in vorticity divergence form, which means that we first have to derive a divergence equation in both cases here. And we know in the divergence equations for the quadrilateral C-grid case, there is an averaged vorticity occurring here in the divergence equation. And for getting or for heading towards the wave equation, we have to replace this averaged theta here by an according vorticity equation. And if we directly write down this average vorticity equation with the same averaging, we can wrap up this 3 equations and just go for the shallow water wave equation and dispersion relation. This is very straightforward in a quadrilateral grid. We can do the same thing also for the hexagonal C-grid, and we write down the divergence equations. And now we have here an theta A, so an averaged vorticity which appears at the same point as the divergence, so in the center of a hexagon. And this theta A here is formed indeed out of these kind of averaged velocities or velocity components. And for doing the same heading towards the shallow water wave equations, we can also write down a vorticity equation in terms of, or averaged to the cell center in the form of a theta A. So, and this is an averaged vorticity here, and now you wonder from which vorticity components is this vorticity formed? So what are the ingredients of this theta A vorticity? And and if you do this and you try to figure out which which vorticity components are forming the theta A vorticities here, you see indeed, okay, you can say this theta A vorticity is an average of these 6 vorticities here at the vertices, but it is not an average of triangular vorticities here. It is in fact an average of vertex vorticities, which are in fact itself formed out of these 3 rhomboids vorticities. And this is the miracle of this hexagonal secret. So the vertex vorticity, which appears here and is comparable to the vertex vorticity which appears here in the quadrilateral secret, this vertex vorticity is formed from these 3 rhomboid vorticities. So the average of the 3 vorticities on rhombi has the same meaning on the hexagonal secret as 1 dual grid vorticity on a quadrilateral grid. So the red box here is comparable to this colored boxes here. So why this is the case? Is there a deeper reason why we indeed see that the vorticity is defined on rhombi instead of triangles? It's we can have another look on the problem. We can say, okay, we want to express a vector field and we do not care about shallow water equations at all. We just care about the representation of a velocity on this kind of hexagonal secret. And therefore we do the Helmholtz decomposition. On a quadrilateral grid, this is very easy to do, but on the hexagonal grid, it turns out to be a bit more difficult because we have, again, to meet the linear dependency constraint. So we have to slave the overspecified vector components, and as I told you before, this is done via this kind of tilde averaging, which results in the fact that if I put the tilde averaging on the first, second, and the third equation and sum them up, it will give 0, so that the proof that those components are linear dependent. If I do this, I also have to, if I do the tilde averaging on this equation, I can guarantee that this term here sums up to 0, but I also have to prove that the first term here, which deals with the stream functions, also sums up to 0. And it is only possible if the stream functions are defined on the centers of the hexagons and not in the corners, and they are averaged first along the grid, and then I take some kind of which I call the St. Andrews cross gradient. And if I now look whether I get that the sum of these 3 equations vanishes when I do this averaging, then I see, okay, that is indeed working. So, and yeah, the Helmholtz decomposition provides a linear dependency of the vector components only if the tilde averaging is used for the stream function, as you can see here. And the stream function is not defined on triangular centers or at the corners of the hexagons, but on the hexagon centers, and occurs always as an average quantity. So if I go now one step ahead and say, okay, I usually when I program a model, I do not need the Helmholtz decomposition. But what I need sometimes is that I have to compute the diffusion. And if I compute diffusion, I have to put a Laplacian operator in front of these equations here, and I arrive at the vector invariant form of the vector Laplace. And in a quadrilateral grid, we know how it works. And on the hexagonal grid, we suddenly see that we need vorticities again on these at the edges and in the centers of these rhomboids. And only then, if I again apply this tilde averaging and sum up, I see that the result is 0 and that my components of this vector indeed are linear dependent. So now let's go more in depth of a model, or more to a more applied part of the talk. Let's consider the momentum diffusion. As I said, if I take the vector invariant form of the vector Laplace, I have to use the vorticities here and the divergence here. I can also take second order finite differences by just taking 1 times the outer values and minus 6 times the inner value. This is very well known, but if I want to compute a physically meaningful divergence of momentum diffusion, then I need to simulate the divergence of a turbulent friction tensor. And if I do that, I cannot use the second order differences and also not the vector invariant form. On general grids, I have to use the form in which the shear deformation and the strain deformation occur, because these are the quantities which enter the turbulent stress tensor. If you are, and this is the Smagorinsky diffusion form. And this is the only, and now the point is that also the shear deformation which enters the Smagorinsky tensor must be defined on this 3 rhomboids. So the vorticity is defined on the 3 rhomboids, and also the shear deformation is defined on the 3 rhomboids. And the point why I have to use this Smagorinsky type of diffusion is that I want to have energy conservation in my model. So I have to model the turbulent friction tensor, and at the same time this friction tensor must be symmetric, because if I add the dissipative heating to the internal energy equation, which is here, I can I must this term here, I must be sure that this turbulent dissipative heating is positive. Otherwise, I would not create entropy. So the second law of thermodynamics asks me to create and not destroy entropy, and therefore I have to make sure that this epsilon is positive, and I can only achieve this if I use this Smagorinsky kind of diffusion. And if I compute this on an arbitrarily shaped hexagonal mesh, I can prove that this is indeed positive in the case when I define the strain shear deformation at the rhomboids, and I also put the diffusion coefficient at the rhomboids, and I can prove that epsilon is positive in the case of equilateral grids. So, and this is a result of the ICON model here, so that I can prove that indeed energy is conserved. Here you can see an experiment with the baroclinic wave. This black line is the total energy, this is the kinetic energy, this is the internal potential energy and internal energy. And this is a run without diffusion, but only until 15 days, because otherwise, if you run it longer without diffusion, the model is no longer stable, because from a physical point of view, all your fronts collapse and you need some diffusion from physical reasons. So if I now run the model for 40 days, you can indeed see the total energy is again conserved, the black line, and how the other energies are evolving. But if you do not feed in the dissipative heating, this is the gray line, and you see that you lose as much energy as you have altered into kinetic energy. So it's quite an error what you are doing if you do not add this frictional heating. You can also run the Hell-Suarez test case, with and without heating, and you see here this is the mean temperature, and the colors are the differences between the run without dissipative heating minus the run with dissipative heating. And you see without heating the atmosphere is a bit colder, and also the mean jets are a bit more to the equator. So now the third part, which is already 5 minutes before the end. It's about the Hollingsworth instability. So when I ran the model for the first time, I ran into this instability which I saw on the for the upward air velocity, so for the vertical velocity, just the baroclinic wave test case. And here I have used the vorticity reconstruction as proposed in the TRIS scheme. And here you see another realization of the same test case, again without diffusion, but with a so-called vertex vorticity scheme. And I will shortly explain you why this vertex vorticity scheme is better. So, the point I want to make is, if you do not make sure that the momentum advection in this form is the same as the momentum advection in the vector invariant form, then you can run into problems. And this was first observed by Hollingsworth and al. In 1983. Suppose that you have an error because your momentum advection form is not the same as the vector invariant form. Then you have an error. The error will alter your balance equation. This is the quasi-geostrophic viewpoint. It will also, already in the quasi-geostrophic viewpoint, will alter your balance equation. And if you rewrite the fluid dynamics equation in this kind of geopotential tendency equation and omega equation, you see that there are errors which are just appearing because you have this non-cancellation errors. And this error will increase if the vertical wind shear increase, because this error depends on the velocity itself. So dp epsilon will be large, and it will also increase if your static stability is decreasing. So you will find the error on this side of the frontal zone, and that's indeed where you will find it if you look at this color here. So we can explain why this Hollingsworth instability occurs. And how to get rid of it, just by observing that Zadurny introduced a scheme which does not have the Hollingsworth instability at all. And this was, and he took just the vertex vorticity here, and the vertex vorticity here, averaged to this point and multiplied with the velocity, with the reconstructed velocity. And by observing that he used just the vertex vorticity, I thought, okay, I also just use the vertex vorticity, but the vertex vorticity, which is the average of the three rhombi. And so I developed a scheme for the generalized Coriolis term, which is very similar to the to this Zadurny scheme, which does not have the Hollingsworth instability, and voila, so that's the result.
Time for a couple of questions.
How does the is this just a modification to the kinetic energy term that's in the?
No, it's a modification to the vorticity term. It's not a modification to the kinetic energy term. So that is what I tried first, and then I realized that you could do it vice versa, not to alter the kinetic energy, but to alter the vorticity term. This is yeah.
The original kinetic energy.
Yes. Yeah. The original attempt to get rid of it was the kinetic energy. Now I turn to.
Wouldn't that interfere with the other aspects that you are modifying the vorticity?
No.
You make the vorticity that you like. Modify.
I do not. I mean, the point is that that in the TRIS scheme, you were using the vorticity from all around the edges here, and not only from the immediate neighbors. So the original proposal by TRIS was to use a vector reconstruction combined with some kind of vorticity to get energy conserving scheme. But it was using all the edges which are around this hexagon. And I figured out how I can get an energy conserving scheme which at the same time does not have the Hollingsworth instability because it uses only the vertex vorticities. So this is a trick. And here you can see the part of the Poisson bracket which does this. It seems to be a bit complicated, but it is, in fact, it is not so complicated if you code it up. So.
John.
Is there a finite element formulation that gives exactly the same thing without all
Oh,
this
I don't know. Sorry.
gymnastic?
I don't know.
Probably questions for one of
Yeah, for someone else.
Maybe for Colin?
For Colin.
Okay, let's finish there. We've got coffee in half an hour, so I just like to thank Alma and all our speakers.